Good evening to all. Is there any disturbance? Is there any disturbance? Audio disturbance? Additional sounds? So for this lead compensator topic, in order to solve the numerical problems, you need similar graph sheet. I hope you people have similar graph sheet in your hands. So let us start the topic. So lead compensator. If any issue is there, just message me in the chat box. I will see. Okay then. So lead compensator. So lead compensator is a compensator which have the characteristics of lead network. Okay, since the lead compensator has the characteristics of lead network, it is called as lead compensator. Okay, so if to this component, if you give any sinusoidal signal to the lead network, then in steady state output, there will be a phase lead with respect to the input. So output, whatever steady state output that is produced here, that output will lead the input. Okay, so whenever sinusoidal input is given. So lead compensator, it increases the bandwidth of the given system, and it also improves the speed of the response, and it also reduces the amount of the overshoot. So it appreciably improves the transient response, whereas there is a small change in steady state accuracy. So there may be small change in the steady state accuracy. Okay. There may be small change in steady state accuracy, but there will be improvement in the transient response. So this lead compensator, it is usually used to make an unstable system stable. Okay, it is used to make unstable system stable, and it is essentially an high pass filter. So it amplifies high frequency noise signals. Since it's a high pass filter, it amplifies high frequency noise signals. If the pole introduced by this compensator, that is lead compensator, is not cancelled by the zero in the given system, then lead compensator will increase the order of the system by 1. Okay, so these compensators, what they do is they will add a pole or zero to the system. So when they add pole and zero to the system, and if the pole is not cancelling the zero, then the order of the system will increase by 1. Now let us see S-plane representation. of lead compensator. How to represent lead compensator on the S plane. So as I said, compensators add pole and zero to the existing system. So since this is a lead compensator, the pole of this lead compensator is S is equal to minus 1 by alpha t, and the zero of this lead compensator is S is equal to minus 1 by t. Okay, pole of the lead compensator is S is equal to minus 1 by alpha t, and 0 of the lead compensator is S is equal to minus 1 by t. So if we plot this pole 0 plot on the S plane, if you locate these poles and zeros, this pole and 0 on the S plane, then this is how it will look like. Okay. So pole of the lead compensator, and this is the pole of the lead compensator, and this is the 0 of the lead compensator. Okay, so the location of pole and 0 on the S plane. So here this alpha is the attenuation term. So this alpha value, it will be less than 1. So let me see whether I can draw alpha. Where is my cursor here? So this alpha, it will be less than 1. Sorry, I am unable to write properly. So alpha will be less than, sorry, alpha will be less than 1. Alpha will be less than 1. So the 0 is closer to the origin. If you see, if you carefully observe here, this is our 0, which is closer to the origin than pole on the negative real axis. So why 0 is closer to the origin and compared to the pole? Why? Because alpha is less than 1. This alpha, which is the attenuation value, which is less than 1. Okay, so let us see the transfer function of this lead compensator. So transfer function of the lead compensator is GC of S. Okay, compensated transfer function is denoted by GC of S. So S is equal, GC of S is equal to S plus ZC by S plus PC, where ZC is the 0 and PC is the pole of the compensator. So what is 0? It is minus 1 by t. So S minus of minus 1 by t is S plus 1 by t. S minus of minus 1 by alpha t is S plus 1 by alpha t. So this is the transfer function of the lead compensator. Okay. So this is the transfer function. Sorry. This is the transfer function of the lead compensator. Okay, where t will be always greater than 0 and alpha will be less than 1. Okay, t will be greater than 0 and alpha will be less than 1. Now we know magnitude of 0. What is magnitude of 0? Zc is equal to 1 by t. So what about t? T is equal to 1 by Zc. Okay, Zc is equal to 1 by t. Therefore, t is equal to 1 by Zc. Okay, if t is equal to 1 by Zc, we can determine the alpha value. Okay, and we also know pole is equal to what? PC of the compensator, that is PC is equal to 1 by alpha t. So where alpha t equal to what? 1 by PC. So if you send t to this side, alpha is equal to 1 by t PC, and 1 by t is nothing but 1 by t is nothing but Zc. So what is alpha? So if you know the 0 value and pole value, okay, so if you know the 0 value and pole value, you can determine the attenuation value, that is alpha value. So alpha is equal to what? Zc by PC. Okay, alpha is equal to Zc by PC. Now let us see the realization of lead compensator using electrical network. So here we are taking RC network here to realize the lead compensator. We are taking RC network. So here EI of S is the input voltage, E naught of S is the output voltage. You can draw the diagram. Draw the diagram. I will give you a minute. Within a minute, you could just draw the diagram. Realization of lead compensator using electrical network. Draw the diagram. As soon as you complete, just inform. Draw with free hand as quickly as possible. Draw it and inform. If there is any disturbance, if my voice is low or if it is not audible, just inform. I hope you have written. Let us proceed further. So here, um, here if I want to determine the output voltage, okay, so I can implement voltage division rule, not current, sorry. So I can implement voltage division rule here. So E naught of T is equal to what? Total voltage EI of E naught of S, sorry. E naught of S is equal to what? Total voltage EI of S into E naught of S is across R2. So self resistance, you can say R2 by R2 plus opposite resistance. What is the opposite resistance? Opposite resistance is the parallel combination of this R1 and 1 by SC. Opposite resistance is the parallel combination of R1 and 1 by SC. So R1 and 1 by SC, they are parallel to each other. So what is the equivalent resistance of this parallel connection? Equivalent resistance is R1 into 1 by SC divided by R1 plus 1 by SC. Of course, here it is, I have written there. Yes, okay, yeah. Yeah, I have written SC and I'm also speaking out SC. It's okay. So this is the parallel combination. So that parallel combination equivalent resistance that is written here. This is the equivalent resistance of this parallel combination. Okay. So R1 into 1 by SC by R1 plus 1 by SC. Okay. So here we are implementing voltage division rule to determine the output voltage. Just rearrange the terms and simplify. E naught of S is equal to EI of S into R2 by R2 plus R1 by R1 SC plus 1. Okay. So just again rearrange and simplify. You will get E naught of S is equal to EI of S into R2 by R2 into R1 CS plus 1 plus R1 by R1 CS plus 1. Okay, so if I want to determine the transfer function for this system, I should take the ratio of output by input. So what is my output? E naught of S. Input is EI of S. So what is E naught of S by EI of S? It is R2 by, okay, it is R2 by R2 into R1 CS plus 1 plus R1 by R1 CS plus 1. That is my transfer function. So again further I can simplify. If I simplify further, I will get E naught of S by EI of S is equal to R2 into R1 CS plus 1 by R2 R1 CS plus R2 plus R1. That is equal to, I have taken common in the numerator, I have taken R1C R2. So I have taken this R1C R2. Therefore, R1C R2 into S plus 1 by CR I will get. And in the denominator, I have taken R1C R2 common. So I have got R1C R2 into S plus R1 plus R2 by R1C R2. Okay. So here this R1C R2, R1C R2, this can be cancelled with this. Okay, what is left over? S plus 1 by CR1 by S by S plus R1 plus R2 by R1C R2. Here once again I have taken 1 by CR1 common. So I have got S plus 1 by R2 by R1 plus R2 into 1 by CR1. Okay. So this is my transfer function. Okay. Now let us compare this transfer function of your electrical network with the transfer function of your, sorry, this is lead, this is not lag. This is lead compensation. Here it is lead compensator, not lag compensator. Okay. I will write here. So there is simply I have copied from the previous lag compensator topic. So that's I forgot to change it. I will write it. It's not lead, it is, this is lead. Okay, so this is lead. So transfer function of lead compensator, just now we have seen in the previous slide, that is GC of S is equal to S plus 1 by T by S plus 1 by alpha T. Okay, so GC of S is equal to what? S plus 1 by T by S plus 1 by alpha T. So you just compare this equation 2 with equation 1. If you compare, what you can see is 1 by C R1 is equal to 1 by T, and isn't it? Okay, you just compare. So 1 by CR1. Here also 1 by CR1 is there. So 1 by T. What is alpha value? Alpha value is R2 by R1 plus R2. Okay, R2 by R1 plus R2 is the alpha value. Okay then. So you just compare. If you compare both, you can determine, you can, if you compare those two, you will get the alpha equation. Okay, you will get the alpha equation. So what is our alpha now? Alpha value is R2 by R1 plus R2. So this is it. Okay, so what is T? R1 into C. Okay, T is R1 into C, and alpha is R2 by R1 plus R2. So now let us see the frequency response of lead compensator. Frequency response of lead compensator. So we know the compensator transfer function GC of S is equal to GC of S. Okay. Are you able to follow? You just mention in the chat box. Are you able to follow or not? GC of S is equal to what? S plus 1 by T by S plus 1 by alpha T. Are you able to follow? Okay. GC of S is equal to S plus 1 by T by S plus 1 by alpha T. So just rearrange the terms and you just take the common denominator of your numerator term. Here if you take common denominator, what will happen? St plus 1 by T. And for the denominator also, you just take the common denominator. What is it? If you take common denominator, you will get S alpha T plus 1 by alpha T. So just rearrange the terms, you will get GC of S is equal to alpha into 1 plus St by 1 plus alpha St. Okay, so this is our transfer function of lead compensator. Okay, this is the transfer function of the lead compensator. Now you can simply, if you want the sinusoidal transfer function, then simply replace S by j omega in the above equation. Replace s by j omega in the above equation, and your transfer function will become sinusoidal transfer function. Just write it down. Okay. Now, you just replace s by j omega, gc of j omega equal to alpha 1 plus j omega t by 1 plus alpha j omega t. Now, if omega equal to 0, what will happen? The compensator, lead compensator transfer function will be equal to the attenuation value, that is alpha. Okay. So, from this equation, that is gc j omega equal to alpha, sorry. So from this gcj omega equal to alpha, what we can say is that the lead compensator provides an attenuation of alpha where alpha is less than 1. Okay, if I don't want this attenuation alpha, then what I should do is I must connect an amplifier. Okay, what I should do is, if I don't want alpha, then what I should do is I must connect an amplifier. Okay, I couldn't write E properly, but if I don't want this alpha, then I should connect an amplifier whose magnitude should be equal to 1 by alpha. Okay. Now, let us assume that we don't want this alpha at all. If we don't want this alpha, then we have to eliminate it. So, let us assume we have connected an amplifier. We have eliminated this alpha value. Then what will happen to our transfer function? Gc of j omega, it will be equal to 1 plus j omega t by 1 plus j omega alpha t. Okay. So, now this is our transfer function of lead compensator without attenuator. Okay. Without alpha. Okay. Without alpha. This is our transfer function of lead compensator. Okay, now this is sinusoid. This is in sinusoidal form. You can determine the magnitude. 1 plus j omega t. What is the magnitude of 1 plus j omega t? It is root of 1 plus omega square t square. What is the angle tan inverse of omega t by 1? Okay, for the denominator, 1 plus j omega alpha t. So what is the magnitude? 1 plus omega square alpha square t square. What is the angle tan inverse of omega alpha t by 1? So we have got the magnitude and we have got the angles for this sinusoidal transfer function. Okay. Now, how many basic factors are there? One numerator, first order derivative factor, and first order denominator factor is there. Okay. So two basic factors are there in this lead compensator transfer function without any attenuator. Okay. So okay, so since there are one first order numerator factor and one first order denominator factor are there, therefore there will be two corner frequencies, omega C1 and omega C2. Okay, there will be two corner frequencies. So what is the corner frequency of this first factor, first order numerator factor? The corner frequency of first order numerator factor is 1 by T. Okay, coefficient of omega is what? T. Therefore, what is the corner frequency? 1 by T. So what is the corner frequency of this first order denominator factor? Coefficient of omega is what? Alpha T. Okay, coefficient of omega is alpha t. Therefore, omega C2 is equal to 1 by alpha t. Okay, 1 by alpha t. So here we have two corner frequencies. One is due to this first factor, first order numerator factor. Another one is due to the first order denominator factor. So 1 by t is one corner frequency, 1 by alpha t is our second corner frequency. Okay. Now here t value is greater than alpha t and omega c1 is less than omega c2. T is greater than alpha t and omega c1 is less than omega c2. Now let us determine the magnitude plot and phase plot for this compensator. Okay, so for that, let us determine the magnitude. What is A? A is the magnitude of sinusoidal transfer function in decibels. Okay, so what is A? Magnitude of G of j omega in decibels. What is the formula? 20 log of the magnitude. Okay, 20 log of, what is the magnitude? Root of 1 plus omega square t square by root of 1 plus omega square alpha square t square. Okay, are you able to follow? Just mention in the chat box so that I will be able to know that you are listening to the class. Are you able to follow or not? Okay, so A is equal to magnitude in decibels, that is equal to 20 log root 1 plus omega square t square by root of 1 plus omega square alpha square t square. Now at very low frequency, at very low frequencies, that is omega value less than omega c1. Okay, at omega less than omega c1. So when frequency is very low, omega t will be very less than 1 and omega alpha t will also be very less than 1. Okay, so when frequencies are very low, at low frequencies, when omega is less than omega c1, then omega t will be very less than 1 and omega alpha t will be very less than 1. Therefore, our factors, that is first order numerator factor and first order denominator factors, if you consider, okay, so 1 plus omega square t square, it will be approximately equal to 1. Okay, and 1 plus omega square alpha square t square, that is in the denominator. Okay, this denominator. 1 plus omega square alpha square t square, it will be approximately equal to 1. Why they are approximately equal to 1? Why? Because omega is very less than, omega value is less than first corner frequency. Therefore, omega t will be very less than 1 and omega alpha t is very less than 1. Now substitute this condition in the above equation. In this equation, if we substitute, so instead of omega square t square, okay, so 1 plus omega square t square is equal to what? 1. So instead of writing 1 plus omega square t square, write 1. Root of 1 is 1. And in the denominator also 1 plus omega square alpha square t square. Instead of writing 1 plus omega square alpha square t square, write 1. So root of 1 is 1. Root 1 by root 1. Okay, so root 1 is 1, root 1 is 1. So 1 by 1 you will get 1. So what you will get? You will get 20 log 1. You will get 20 log 1. So 20 log 1 is equal to 0. So A value, where is my cursor? Yeah, A value when omega is less than first corner frequency, at low corner frequency, A value is equal to 0. Now let us assume that frequency is in between omega c1 and omega c2. Means the frequency range is between omega c1 and omega c2. If the frequency range is in between omega c1 and omega c2, then omega t will be greater than 1 and omega alpha t will be less than 1. Okay, set this condition. Omega t will be greater than 1 and omega alpha t is less than 1. Therefore, 1 plus omega square t square will be approximately equal to omega square t square, because omega t is greater than 1. 1 plus omega square t square is equal to omega square t square. And another condition is omega alpha t is less than 1. Therefore, 1 plus omega square alpha square t square will be approximately equal to 1. Why? Because omega alpha t is less than 1. So, therefore, substitute this above condition in this magnitude equation. So instead of writing 1 plus omega square t square, write only omega square t square. So you just erase this. So you just remove this. Okay, similar, instead of writing 1 plus omega square alpha square t square, write only 1. So you can remove this. So what is left over? 20 log root of omega square t square by root of 1. That's what is, will be left over. Okay. So what is A now? A is equal to 20 log root of, I'm sorry, here I didn't change this. This is it. So 20 log A is equal to A is equal to 20 log root of omega square t square by 1. Omega square t square root of 2 omega square t square is nothing but omega t. So 20 log omega t you will get. 20 log omega t by 1 I have written, but no need to write 1. So A value within the range of omega c1 to, when frequencies are within the range of omega c1 to c2, A value is equal to 20 log omega t. Now let us consider. Okay. Now let us consider high frequencies, means frequency above omega c2. So when frequencies are above omega c2 at high frequencies, omega t will be very, very greater than 1 and omega alpha t will be very, very greater than 1. So when omega t is very, very greater than 1 and omega alpha t is very, very greater than 1, therefore 1 plus omega square t square will be approximately equal to omega square t square, and 1 plus omega square alpha square t square will be approximately equal to omega square alpha square t square. Okay. When omega t is very, very greater than 1 and when omega alpha t is very, very greater than 1, 1 plus, where is my cursor? 1 plus omega square t square will be approximately equal to omega square t square, and 1 plus omega square alpha square t square is approximately equal to omega square alpha square t square. Okay. So substitute that condition in this equation. So A is equal to 20 log root of 1 plus omega square t square by root of 1 plus omega square alpha square t square. So substitute the above condition in this equation. In this equation substitute, what do you get? 20 log root of omega square t square by root of omega square alpha square t square. Root and square will cancel. What is left over? 20 log omega t by omega alpha t. So this omega, this t and this t, they will be cancelled. What is left over? 20 log 1 by alpha. Okay. So at high frequencies, okay, at high frequencies, A value is a constant value, we can say. There is no t term. Okay, there is no variable term. Omega t means it will vary. Okay, so it is constant. At high frequencies, A value is constant, and at low frequencies, at very low frequencies, what is A? A is 0. At low frequencies, A is 0. Okay, at low frequencies, A is 0. At high frequencies, A is 20 log 1 by alpha. In between, when frequencies are in between, A will vary. There is cursor, I am unable to find. A will vary as omega t varies. Okay, as omega t varies, A will vary. Okay, so if we plot the magnitude plot, you can see here at low frequencies, magnitude. Okay, this is our magnitude. Okay, with respect to what? With respect to omega. With respect to omega, I have plotted here. Okay, magnitude with respect to omega, x-axis omega and y-axis magnitude. So at low frequencies, magnitude is 0. At high frequencies, magnitude is 20 log 1 by alpha. Okay. So in between, what will happen? The magnitude will gradually increase. In between, with respect to omega, the magnitude will gradually increase. Okay. So this is about magnitude. Let us see the phase. Okay, so what about the phase? What is phase? It is the angle of j omega. That is tan inverse of omega t minus tan inverse of omega alpha t. So if you remember this equation number 4, okay, what is it? Tan inverse of omega t by tan inverse of omega alpha t. So you can rewrite it as tan inverse of omega t minus, you can minus tan inverse of omega alpha t. Okay, that's what is written here. Okay, tan inverse of omega t minus tan inverse of omega alpha t. Now just assume, just consider omega tends to 0. If omega tends to 0, substitute 0 in the above equation, you will get phi equal to 0, and substitute omega equal to infinity in the above equation, you will get omega phi equal to 0. Okay, for omega tends to 0 and omega tends to infinity, phase is 0. Okay, so we can say that as omega is varying from 0 to infinity, phase angle increases from 0 to, of course, by looking at those two cases, by looking at these two cases, we can't say that phase angle increases. Okay, we can't say that phase angle increases, but we have to substitute some other value in between 0 and infinity. If we substitute some other value, what we can see is that the phase angle phi will increase. Okay, uh, at omega equal to some omega m. Okay, at omega, okay, at omega equal to some omega m, the phase angle, I have not substituted here, you substitute some value here. Okay, instead of omega you just substitute 1 by t. Okay, t will be cancelled. Okay, and here also you just substitute instead of omega, substitute alpha t. Alpha t will tan inverse of 1 you will get, tan inverse of 1 you will get. Okay, so when omega is equal to omega m, I can show you in the plot. When omega equal to omega m, what will happen is the phase will gradually increase, and at omega m, till omega reaches its omega m value. Okay, so I think you won't be able to understand if you look at this. So see here, at low frequencies, at omega equal to 0, phase angle is 0. At omega equal to infinity, phase angle is again 0. But in between, okay, in between, when omega equal to some omega m, the phase angle is becoming maximum. Okay, the phase angle is becoming maximum. So to know at what omega, what is this omega m value, to know what is this omega m value, what we have to do is we just consider the corner frequencies. We have two corner frequencies, isn't it? We have two corner frequencies. Consider both the corner frequency values. What is the corner frequency values? Omega c1 is 1 by t and omega c2 is 1 by alpha t, and you just multiply and take the square root of it, omega m, you will get the omega m value, maximum phase lead value. You will get it by taking the square root of the corner frequencies, multiplying them with each other. So if you do that, you will get omega m equal to 1 by t root alpha. Okay, so if you see the plot, so at omega m value is what? 1 by t root alpha. So the phase will be maximum. The phase of the lead compensator will be maximum. Okay, so this choice of this alpha value, it is actually governed by the inherent noise in the control system. So how much alpha should be there? So depending on the inherent noise, we will decide. Okay. So in lead compensator, actually high frequency noise signals are amplified by a factor of 1 by alpha. Okay, so high frequency signals, they will be amplified by a factor of 1 by alpha. So if you represent that in decibels, it should be equal to 20 log 1 by alpha. Okay, So usually the typical choice of alpha value is around 0.6. Okay. So you can see here I have written phi m, maximum phase is obtained at omega m. So at omega m you can determine if you know the corner frequencies. So let us see how to determine this omega m, phi m and alpha theoretically. So if we want to determine omega m, then what we have to do is just differentiate phi by omega and equate it to 0. Okay, differentiate phi by omega and equate it to 0. So what is our phi? Phi is tan inverse of omega t minus tan inverse of omega alpha t. Take it, differentiate it with respect to omega. Okay. So if we differentiate it with respect to omega, what you will get is d phi by d omega equal to 1 by 1 plus omega t square into t minus 1 by 1 plus omega alpha t square into alpha t you will get. Okay, so if we differentiate this above equation with respect to omega. Okay, so after differentiating phi with respect to omega, just assume we want the maximum value of omega. So consider omega equal to omega m. So when omega equal to omega m, d phi by d omega we should be equal to 0. Okay. So equate that above equation to 0 and just simplify it. Okay, 1 by 1 plus omega m whole t square into t minus 1 by 1 plus omega m alpha t whole square alpha t is equal to 0. Send this term to the right side. So what do you get? 1 by 1 plus omega t square t equal to 1 by 1 plus omega m alpha t square alpha t. This is what you will get. Now just cross multiply both the terms. After cross multiplication you will get 1 plus omega m alpha t square is equal to alpha into 1 plus omega t square. Okay. And after cross multiplication, you just rearrange the terms. You will get omega m alpha t square minus alpha omega m t square is equal to alpha minus 1. Just simplify it. You will get omega m is equal to 1 by t root alpha. Okay. So omega m is 1 by t. It is same as what we have got earlier by simply taking the square root and multiplying the corner frequency values. Same formula, isn't it? You will get the same formula. Okay. Now let us consider the phase angle phi. What is it? Tan inverse of omega t minus tan inverse of omega alpha t. Now take tan on both sides of this. So phi is there on left side. So tan phi. On right side tan into tan inverse of omega t minus tan inverse of omega alpha t. Okay. So simply we have taken the phase angle. This is our phase, isn't it? This is our phase. Just multiply tan to left side and the right side of the above equation. Okay. Take phase, multiply tan to the left side and right side of this above equation. Just multiply tan to the left side and right side of the above equation. And we know one formula. What is it? That is tan a minus b is equal to what? Tan a into tan b by 1 plus tan a into tan b. So just implement that condition, that formula in the above equation. You will get tan phi is equal to tan of tan inverse omega t minus tan of tan inverse omega alpha t by 1 plus tan of tan inverse omega t by tan of tan inverse omega alpha t. Just simplify it. You will get tan and tan inverse will be cancelled actually. Tan and tan inverse will be cancelled. So what is left over now? So tan phi is equal to what? Omega t minus omega alpha t by 1 plus alpha omega t square. Okay. 1 plus alpha omega t square you will get. So now when omega equal to omega m, phi is equal to phi m. Okay, when omega equal to omega m, phi equal to phi m. So consider, write type tan phi as tan phi m. Instead of omega, write omega m t minus omega m alpha t in the above equation by 1 plus alpha into omega m t square. Okay, so this is omega subscript m. Okay, now what is omega m? 1 by t root alpha. So instead of omega m, write 1 by t root alpha. Instead of omega m, write 1 by t root alpha into t minus 1 by t root alpha alpha t by 1 plus alpha into 1 by t root alpha into t whole square. So just simplify it. You will get 1 by t root alpha t into 1 minus alpha by 1 plus alpha into 1 by t root alpha t whole square. Okay. So simple mathematical simplification, nothing technical here. Okay. So if you know this formula, this above formula, you can easily determine, you can simplify all these terms easily. Okay, so now tan phi m. Okay, this is tan phi m. Tan phi m. Tan phi m is equal to what? This is tan. This is tan phi. Okay, tan phi m is equal to what? 1 by t root alpha into t into 1 minus alpha by 1 plus alpha into 1 by t root alpha t whole square. So just simplify, you will get 1 by root alpha into 1 minus alpha by 1 plus 1. So further if you simplify, cursor, yeah, you will get tan alpha, tan phi m is equal to 1 by alpha by 2 root alpha. So what is maximum lead angle, not a lag angle, sorry. So maximum lead angle phi m. So maximum lead angle phi m is equal to tan inverse of 1 minus alpha by 2 root alpha. So this is phi m formula. Just write it down. Are you able to follow? Is there any disturbance? Okay. Now let us find the value of alpha. Let us find the value of alpha from phi m. Okay, value of alpha from phi m. So from this phi m equation, okay, from the phi m equation, so what we can say is that we can represent, so from the above equation, it is phi m is equal to what? Tan inverse of, cursor. So phi m is equal to tan inverse of 1 by tan inverse of 1 minus alpha by 2 root alpha. So you can represent 1 minus alpha and 2 root alpha as the sides of your right angle triangle. Okay, so what is it? 1 minus alpha is the opposite and 2 root alpha is the base. Okay, so 1 minus alpha is the opposite value of your right angle triangle and 2 root alpha is the base, and phi m is the angle. Phi m is the angle. Okay, I have a laser here. Phi m is the angle. Now, for this right angle triangle, just simplify the right angle triangle to determine the hypotenuse. What do you get? AC, A, B, and C. Okay, A, B, C. So, what is AC is equal to root of B square plus AB square. What is BC? 1 minus alpha square, and AB is root 2 root alpha square. Okay, so just to simplify it, you will get AC is equal to 1 plus alpha. This is our AC value, which is 1 plus alpha. Okay, so now we know the hypotenuse value. We can determine the sine phi m value. What is sine phi m? Sine theta is equal to what? Opposite by hypotenuse. Opposite was 1 minus alpha, and hypotenuse is 1 plus alpha. So sine phi m is equal to sine phi m. Uh, Sine phi m is equal to what? 1 minus alpha by 1 plus alpha from the right angle triangle. Okay, so uh, sine phi m into 1 plus alpha is equal to 1 minus alpha. Just rearrange the terms and simplify. You will get sine phi m plus sine phi m alpha equal to 1 minus alpha. And alpha plus sine phi m alpha is equal to 1 minus sine phi m. So here I have taken alpha common. If you take alpha common, you will get 1 plus sine phi m equal to 1 minus sine phi m. Okay, so from this you will get the alpha equation. So what is alpha? 1 minus sine phi m by 1 plus sine phi m. So it's a simple mathematical simplification. I hope you are able to follow, whoever is listening to the class. If you are okay, so if you are listening to the class, definitely you will be able to follow simple mathematical simplification. Nothing complicated. Nothing complicated is there. Okay, so let us solve a numerical problem. So to solve the numerical problem, so you need a similar graph sheet. So you just take the similar graph sheet, and I will just go to some other. So this is the numerical problem. So write down the numerical problem. Write down the question. Design a phase lead compensator for the system shown in the figure to satisfy the following specifications. Okay. So we have to design phase lead compensator for the system. Okay, to satisfy the following specification. What are the specifications? Phase margin of the system should be greater than or equal to 45, and steady state error for unit ramp input is less than or equal to 1 by 15, and crossover frequency must be less than 7.5 radians per second, omega gc. Omega gc should be less than 7.5 radians per second, and steady state error for unit ramp input should be less than or equal to 1 by 15, and phase margin of the system should be greater than or equal to 45 degrees. Okay, write down the problem. Write it down as soon as you complete inform. So this is the given system, that is k by s into s plus 1 is the open loop transfer function, and you can see here it is a unity feedback system. It is a unity feedback system. So they didn't mention means they didn't specifically mention g of s uh, in the question. Simply they have given the block diagram here, and unity feedback system diagram has been given here. If you complete inform, okay then. Okay, let us proceed. Now let us see step 1. Calculation of gain k. Okay. Okay, step 1. Sorry. Calculation of gain k. Calculation of gain k. Here, in the question they have mentioned steady state error for unit ramp input is less than or equal to 1 by 15. So ESS is less than or equal to 1 by 15 for unit ramp input. And we know the velocity error constant kV is equal to 1 by ESS. So ESS is equal to 1 by 15. Therefore, velocity error constant kV is equal to 15. Okay, so kV is equal to 1 by ESS. So kV value will be equal to 15. So we already know that. 1 second. So here these cursors. There should be a cursor here. Yeah, this is it. Now here we already know kV is equal to what? Limit s tends to 0, s g of s h of s, where h of s is 1 based on the diagram that has been given. We can say h of s is 1. So kV is limit s tends to 0, g of s, g of s, h of s. H of s is 1. Therefore, what is kV? kV equal to limit s tends to 0, s, g of s. So what is g of s? It is k by s into s plus 1. So s cancel, isn't it? S cancel. Limit s tends to 0, substitute here. Limit s tends to 0, k by 0 plus 1 you will get. So what is kV? kV is equal to k. Write it down. kV is equal to k. So the kV is equal to k. What is kV value? kV value is 15. Okay, kV value is 15. And here what did we get? Here we have got kV is equal to k. Okay, so simple, it's a simple mathematical simplification here once again. So nothing much complicated. So we have got velocity error constant is equal to k, so k value is 15. Write it down quickly. Now, let us proceed further. So let us draw the Bode plot for uncompensated system. So what is our g of s? K by s into s plus 1. So you can rewrite it as, 1 plus s, isn't it? You can rewrite it. It has become an image here. So, okay. So you just rewrite it as 1 plus s. If you rewrite it as 1 plus s, so, and if you replace s by j omega, so this is what you will get. So this is what you will get. So it is k by s into s plus 1. So I want in the basic 1 plus omega t term, or 1 plus st form, 1 plus st form. So I have simply shifted, shifted the positions of s and 1 plus s. Instead of writing s plus 1, I have written 1 plus s. Now, if you write here 1 plus s, if you replace s by j omega, okay, if we replace s by j omega, so instead of s, write j omega. So here I have interchanged these two positions, so I have got 1 plus j omega. So k by g of j omega is equal to what? K by j omega into 1 plus j omega. What is k value? 15. So what about g of j omega now? What is g of j omega? G of j omega is equal to 15 by j omega into 1 plus j omega. Just write it down. If you complete in form. Okay then. Now let us go for the magnitude plot. Now how many factors do we have here? How many factors? One integral factor. So let us see the last equation. One integral factor and one first order denominator factor. Two factors we have. So for first order denominator factor, we can determine the corner frequency. So what is corner frequency formula? Omega c equal to 1 by t. So omega c equal to, what is t value here? Here only 1. What is the coefficient of omega here? Coefficient of omega is 1. So, 1 by t. T value is 1. So, omega c1. No need to write c1 here. Why? Because we have only one corner frequency. So, simply writing omega c is more than sufficient. Okay. Simply writing omega c is more than sufficient. So omega c equal to 1 by 1, that is equal to 1 radian per second. So corner frequency, what did you get? Corner frequency omega c equal to 1 radian per second. Now let us, in order to plot the magnetic plot, let's draw a table. In that table, write down both the factors. One integral factor, that is 15 by j omega. Another factor is first order denominator factor, 1 by 1 plus j omega. So what is the corner frequency for the integral factor? Integral factor will not have any corner frequency, just leave it. Corner frequency of this first order denominator factor, what did we get? 1 radian. So omega c, now once again, here I have written C1, omega c. So omega c is equal to 1. Now what is the slope of the integral factor? Minus 20. Slope of first order denominator factor is minus 20. Okay, so write down the slopes. After that, so send the slope. Okay, change in the slope for always for first factor. There will not be any change in the slope for the first factor. Now send the slope of first factor to the next factor under this column, change in slope column. Just send this here and add it with the slope of this factor. So slope of the previous factor is minus 20, slope of this factor is minus 20, just add it, minus 20 minus 20, you will get minus 40. Just draw the table, write it down. As soon as you complete, inform. Okay then. Now let us consider some low frequency omega L. Low frequency omega L such that omega L is less than omega C1 first corner. Okay, we have only one corner frequency. So I have from previous problem I have copied and I didn't change it. Okay. So let us consider a low corner frequency omega L which is less than omega C, and let us also consider a high frequency which is greater than the corner frequency. So let us consider low frequency and high frequency. Low frequency is omega L, high frequency is omega H. Omega L is less than omega C, omega H is greater than omega C. What is omega C? What is omega C? If you are listening to the class, just mention in the chat box what is omega C value. Omega C value is 1 radian per second. Omega C value is 1 radian per second. So omega C value is 1 radian per second. So assume omega L value less than 1. So omega L value I have assumed here 0.1 radian per second, and omega H value I have assumed 10 radian per second. Omega L is 0.1 radian per second, omega H is 10 radian per second. So what is the formula for magnitude A is equal to magnitude of G of j omega in decibels? Okay, magnitude is A is magnitude of G of j omega in decibels. So let us determine A for all these frequencies. How many frequencies do we have? Three frequencies, omega L, omega C1 and H. Omega L is 0.1 radian, omega H is 10, omega C, not C1, it is C. Okay, it is omega C, not C1. Of course, notations are our wish. We can write any notation. Okay, no need to write omega C1. Simply writing omega C is more than sufficient. So what about the A value? For omega equal to omega L. So when omega equal to omega L, A is what? 20 log of the integral factor. Write down the integral factor 15 by j omega. So what is omega? Omega is here, omega L, that is zero point 0.1. So 15 by 0.1, substitute it here. 20 log 15 by 0.1, you will get 44 decibels. Okay, 20 log 15 by 0.1, you will get 44 decibels. So let us go to the next. Now let us consider omega equal to omega C. So again and again I have written omega C1. Here we don't have more than, we have only one corner frequency, so no need to write omega C1. So this is it. So I have written omega C1. So I just removed that one value, 1. So when omega equal to omega C, A is 20 log 15 by j omega. So what is omega value? Omega C. Omega C is 1. So 20 log 5. 20 log 5 is just simplify, you'll get 24 decibels. Now A value is 24. Next, consider omega equal to omega H. Oh, what is omega H value? What is omega H value? 10 radians. Okay. So for that, formula is slope from omega C to omega H log omega H by omega C plus A at omega equal to omega C. So what is slope from omega C to omega H? What is slope from omega C to omega H? So from omega C to omega H, what is it? Minus 40. Minus 40 is the slope from omega C. This is omega C, isn't it? So from omega C to omega H is next level. Here we didn't write it. But at omega equal to omega C, what is the slope here? Minus 40. So slope from omega C to omega H is minus 40. So where is my cursor? Yeah. So it is minus 40 into log. Omega H value is 10. Omega C value is 1. So log 10 by 1 plus A at omega equal to omega C. So what is A value? At omega equal to omega C, what is A value? 24. Just write 24. So minus 40 into log 10 by 1 plus 24. So just simplify it, you will get minus 16 decibels, A value. So we have got 3 points for A. For omega equal to omega L, for omega equal to omega C, and for omega equal to omega H, we have got 3 values for A. So what is it? A is equal, or for omega equal to omega L, A is what? A is 44 decibels. Okay. So for omega equal to omega C, A is 24 decibels. For omega equal to omega H, A value is minus 16 decibels. So since we have got 3 points, consider A, B, C. Okay. So for omega L, omega C and omega H, consider 1 unit is equal to 10 decibels on y-axis of your similar graph sheet. 1 unit is equal to 10 decibels. Now, at a time I have even considered the phase also here. Instead of going for magnitude plot, I have even considered the phase. What is the phase angle here? For integral factor? Cursor, yeah. What is phase phi? Angle of g of j omega. What is it? For integral factor, phase is minus 90. And the first order denominator factor, It is minus tan inverse of omega for this. Okay, where is it? This is it for this. Okay, for integral factor, angle is minus 90. For first order denominator factor, what is it? Tan inverse of omega. So, so minus tan inverse of omega. So that is it. This is it. Minus 90 minus tan inverse of omega. This is our phase. So for different angles of omega, okay, this is our phase. So for different values of omega, let us find the phase. So for different values of omega, I have considered omega. This is my omega column. This is my phase column. So I'm giving some notations to each and every point on the similar graph sheet. So I'm giving some notations here. So omega I have considered. Omega I have considered. Where is my cursor? Yeah. Point 0.1, point 0.5, 1, 2, 5 and 10. For point 0.1, my phase is 96 minus 96 degrees. For point 0.5, minus 117 degrees. For 1, it is minus 135. Okay, so for 2 it is minus 153. For 5, omega equal to 5. Angle is minus 169. For omega equal to 10, angle is minus 174. Okay, these are my phase angles. I have given some notation E, F, G, H, I, J, some points. Okay, and I have assumed 1 unit equal to 10 degrees on y-axis. Write it down. Now this is our graph. For magnitude, I have considered 1 unit equal to 10 decibels, and for y-axis, I have considered 1 unit equal to 10 degrees. So you can see here, this is my A in decibels. So I have considered 50, 40, 30, 20, 10, 0, minus 10, minus 20, minus 30, minus 40, and minus 50. This is the y-axis scale of A in decibels. Next on for phase. For phase, I have considered minus 180, minus 170, minus 160, minus 150, 10-degree difference, minus 140, minus 130, minus 120, minus 110, minus 100, and minus 90. Okay, on right side, write it down, write down the phase. On left side, write down the A value. This is phase in degrees. And on semilog x-axis, see this is point 1. If this is point 1, point 2, point 3, point 4, point 5, point 6, point 7, point 8, point 9, 1. If this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If this is 10, then this is 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay. If this is 100, this will be 1000. Okay. This will be 1000 if that is 100. Okay, then plot the magnitude plot. You have magnitude and phase plots, isn't it? You just plot the magnitude as well as phase plot. This I will show you the magnitude plot first so that you will not confuse. This is the magnitude plot. Point A, point B, and point C. So what is this point A? Point A is 44 decibels. You just see here. This is what is omega L value? Omega L value is zero point 0.1. This is omega L is zero point 0.1. So for zero point 0.1, this is my minus, not, is it minus? No, plus. It is 44 decibels. Okay. Next, when omega equal to omega C. So when omega equal to omega C, what is omega C value? 1. So what is my 1? This is 1. This is 1. For omega equal to omega C at 1. So what is my magnitude? 24 decibels. So here, this is it. This is 24 decibels. Next, for omega equal to omega h, that is 10. For 10, what is A value? Minus 16. So this is minus 16. Okay, minus 16. So for this is my magnitude plot for my point 1. Okay, for point 1. Okay, for point 1, omega equal to point 1, 44 decibels. For omega equal to 1, wait, where is my cursor and all laser? Okay, so for omega equal to point 0.1, this is 44 decibels. For omega equal to 1, this is 24 decibels. For omega equal to 10, this is minus 16 decibels. This is my magnitude plot. Draw it quickly. Okay, then. I hope you have drawn. So phase plot. So for different omega values, what are our omega values? Where is my cursor? Yeah. So for point 0.1 omega, what is phase? It is minus 9. Sorry, phase it is this point. This is minus 96. Okay. So point for point 0.5. This is point 0.2, point 0.3, point 0.4. This is point 0.5. 0.5. So for point 0.5, what is phase? This is my phase point. How much is it? Minus 117. Okay. So for 1. So 1 is, this is 1. So for 1, what is phase? For 1, phase is, phase, so phase is minus 135. Okay. Next omega value is 2. So if this is 1, this is 2. This is 2. For 2, what is phase value? It is minus 153. Next is 5. It is 2. This is 3, 4. This is 5. Okay. This is 5. So for 5, omega equal to 5, what is phase? Is minus 169. This is minus 169. Next, omega equal to 10. This is 10. For omega 10, my phase is minus 174. Okay. So for these phase values, and for where is it? Yeah. For these omega values, okay. So these are the points that I have got. Join all the points, you will get the phase plot. This is the phase plot. This is the magnitude plot for the uncompensated system. Draw it quickly. I hope you have completed. So now let us see step number 3. Mm. Step number 3, determination of phase margin of uncompensated system. So let us consider 5GC. Okay, 5GC is the phase of G of j omega at gain crossover frequency. Means 5GC is the phase at omega equal to omega GC. Okay, and gamma is the phase margin of uncompensated system. So 5GC is the phase at omega GC and gamma is the phase margin of uncompensated system. Okay, now from the Bode plot, let us determine this 5GC. Okay, so let us go to the Bode plot. Now, if you observe here, Bode plot, I want omega GC, isn't it? So you can get omega GC at 0 decibels. At 0 decibels. Where is 0? This is 0. Okay, this is 0 decibels. So from 0, draw a dotted line towards your magnitude plot. From 0, draw a dotted line towards your magnitude plot. It will intersect the magnitude plot at some point. Here you can see it has intersected the magnitude plot at some point. From the magnitude plot, draw a vertical line towards the x-axis. Okay, so from this wherever this 0, from 0, whatever horizontal line that you have drawn, it intersects the magnitude plot at some point. From that point, draw a vertical line towards the x-axis. Wherever it intersects the x-axis, that is our omega GC. Okay, so while reaching this x-axis, if you see this dotted line has crossed the, it has passed through the phase plot, isn't it? This pink dotted line. Okay, this pink dotted line, it has passed through the phase plot. So wherever it intersects the phase plot, from there, okay, draw a dotted line towards the right side, towards the scale of your phase in degrees. So draw a dotted line towards the phase of your this phase scale wherever you are written, horizontal line towards the phase scale. So you will get 5GC. Okay. So to determine 5GC, what you have to do is you must know omega GC. Okay. To determine 5GC, you must know omega GC. To determine 5GC, you must know omega GC. To know omega GC, what you have to do is you must, omega GC is obtained at 0 decibels. Okay, so from 0, draw a dotted line towards the magnitude plot. It will intersect magnitude plot at some point. From there, draw a vertical line towards the x-axis. So while traveling towards the x-axis, wherever it intersects your x-axis, that is your omega GC. And while traveling towards x-axis, this dotted line will intersect the phase plot at some point. From that point, draw a horizontal line towards the scale of your phase. Okay, so this dotted line, wherever it intersects your scale of your phase, that point is your 5GC. So my 5GC, so my 5GC is minus 167 degrees. Draw it quickly. Now we have got 5GC value. Okay. Now let us determine the gain margin. I'm sorry, phase margin, not gain margin. Okay, let us determine the phase margin of uncompensated system. So what is the formula for phase margin? 180 degree plus 5GC. What is 5GC minus 167? So 180 minus 167, you will get 13 degrees. Okay. So this is our phase margin. But in our question, in the given question, they have asked us that, they have told us that in the question it is mentioned that, let us go back to the question. It is mentioned that phase margin of the system should be greater than or equal to 45 degrees. Okay. Phase margin of the system should be greater than or equal to 45 degrees. That's what is mentioned in the question. But what did we get now? How much phase margin did we get? 13 degrees. Okay. In the question, they have asked us, they have told us that phase margin should be 45 degrees, but we have got 13 degrees. So we need lead compensation to improve the phase margin. Okay. Now we need lead compensator to improve the phase margin. So let us go to the next step now. Step number 4, determining the amount of phase lag to be controlled by the lead network. Okay. Step 4, to determine the amount of phase lag to be controlled by the lead network. So what is our desired phase margin? Desired phase margin. What is our desired phase margin? Desired one, gamma d, is greater than equal to 45 degrees. So since we are going to provide an phase lead, we are going to shift the position of omega gc from its actual position to get the required phase margin. Therefore, additional phase lead is required. Why? Because we are going to shift the position of omega gc. Okay, because of this phase lead. So additional phase lead is required. Consider that additional phase lead epsilon is equal to 5 degrees. Okay, additional phase lead, that is epsilon equal to 5 degrees. So now maximum phase lead angle phi m, let us assume phi m is the maximum phase lead angle, that will be equal to desired one minus the desired phase margin minus the phase margin that you have got for uncompensated system plus the additional phase lead. Okay. So the maximum phase lead angle will be equal to the desired phase margin minus the phase margin of uncompensated system plus the phase lead, additional phase lead. So what is desired one? 45. What did you get for uncompensated system? Phase margin minus 13. What is the additional phase lead? That is 5 degrees. So just simplify it, you will get 37 degrees. Phi m value is what? 37 degrees. Okay, just write it down. Okay, now let's go to step number 5. Step number 5. Determine the transfer function of lead compensator. So what is alpha? We already know the formula, that is 1 plus sin phi m by 1, 1 minus sin phi m by 1 plus sin phi m. Phi m value just now we have calculated 37 degrees. Substitute phi m value here, 1 minus sin 37 by 1 plus sin 37 degrees. Just simplify it, you will get alpha equal to approximately 0.25. Now when omega equal to omega m, dB magnitude of g of j omega. Okay, that is A at omega equal to omega m is equal to, okay, minus 20 log 1 by root alpha. Okay, so when omega equal to omega m, what is A? Minus 20 log 1 by root alpha. So what is alpha value? 0.25. Substitute that in this equation, you will get A value at omega equal to omega m is minus 6 decibels. Okay, A value at omega equal to omega m is minus 6 decibels. Now, do we know the omega m value? We don't know omega m value, but what we know is A at omega m is minus 6 decibels. So let us go to the graph. Just write it down. Inform as soon as you complete. Now we have A value. Now let us go to the graph and determine omega m value. Okay, so here you can see this is minus 6. From minus 6, draw a dotted line towards your magnitude plot. Wherever it intersects, draw a vertical line towards the x-axis. You will get omega m value, that is 5.6 radian per second I have got. Okay, so this is our A value of minus 6. So A value is minus 6 at omega equal to omega m. So from minus 6, wherever minus 6 is there, draw a dotted line towards this magnitude plot. Wherever it intersects, from there draw a vertical line. Wherever it intersects the x-axis, that is our omega m. Okay, draw this dark blue line, dark blue dotted line, whatever you can see. So write down, locate this m, and this is A at omega equal to omega m. Okay, so we have got omega m value. Let us move further. So what is omega m value? It is 5.6 radians, and we know T is equal to 1 by omega m root alpha. Omega m, from the graph we have got 5.6 radians. Alpha is 0.25, we have already calculated. So what is T? It is 0.36. T value is 0.36. Now What is the transfer function of lead compensator GC of S equal to S plus 1 by T by S plus 1 by alpha T? Just rearrange the terms. What is it? Alpha into 1 plus ST by 1 plus S alpha T. You know T value? You know alpha value. Substitute it and simplify. You will get this equation. Okay, this is the equation that you will get. Just write it down. Now, step number 6. Open loop transfer function of compensated system. So, what is our GC of S? It is 0.25 into 1 plus 0.36 S by 1 plus 0.09 S. So, what is our transfer function G of S? What is it? 15 by S into S plus 1. Okay. So, here we have an attenuator value. If we don't want attenuator, what we have to do is we have to connect an amplifier. So, this is our amplifier value. Okay. So, this is amplifier block. This is our GC of S. This is G of S. So this is the lead compensator. When you have connected here, you can connect compensator series or parallel. Here we are showing series connection. Okay, so this is our whole system along with the lead compensator. Okay, so draw it. Okay then. Hmm. Now open loop transfer function. What is the open loop transfer function here? Okay, G naught of S is 1 by alpha into GC of S into G of S. What is 1 by alpha? 1 by 0.25. GC of S is what? 0.25 into 1 plus 0.36 S by 1 plus 0.09 S. What is G of S? 15 by S into S plus 1. Just simplify it, you will get G naught of S. Okay, open loop transfer function of compensated system. What is it? 15 into 1 plus 0.36 S by S into 1 plus 0.09 S into 1 plus. Yes, just write it down. This is the open loop transfer function of compensated system. Okay. Now let us draw the Bode plot for the compensated system. Step number 7. Draw the Bode plot of compensated system to verify the design. Okay. So just replace S by j omega in the above equation. You will get G naught of j omega equal to 15 into 1 plus 0.36 j omega by j omega into 1 plus 0.09 j omega into 1 plus j omega. So just see how many factors do we have. We have an integral factor, one first order numerator factor, One first order denominator, one more first order denominator. Total 1, 2, 3, 4. Four factors are there. Okay, one integral and two first order denominator and one first order numerator factor is there. So for this first order numerator and denominator factors, we can determine the corner frequencies. Total 3 corner frequencies we will get. So what is corner frequency formula? Omega c equal to 1 by t. So what is t value here in this? What is t value in this first order numerator factor? T value is 0.36. So omega c1, okay. I have first considered this point 1. Okay. I have considered first this factor. So what is the coefficient of omega here? 1. So omega c1 equal to 1 by 1. You will get 1 radian per second. Next, I have considered the numerator factors. What is the coefficient of omega? 0.36. So omega c2 I have considered 1 by t value, that is 0.36. I have got 2.8. Later I have considered omega equal to, where is it? Omega coefficient of omega is 0.09. So 1 by omega c3 is 1 by 0.09. I have got 11.1 radian per second. So why the reason why I have not considered first of all omega c1 equal to 1 by 0.36, the reason behind that is to get the sequence means in increasing order. I want omega c1 to be less than omega c2 and omega c2 to be less than omega c3. So I wanted the sequence. So first of all, you just calculate the corner frequencies. Whichever corner frequency is smaller, so you can see the corner frequency of this factor is the smallest corner frequency. That's why you consider that as omega c1. Later, whichever corner frequency is just larger than the previous one, you just consider it as omega c2, and the largest corner frequency you consider as the omega c3. So I hope you have understood. The corner frequency notations should be given in increasing order. Okay. So to you just calculate the corner frequencies for the terms that have been given. Okay, for these terms. Okay, for these terms, calculate the corner frequencies and write down in sequence. Increasing order, omega c1 should be the least and omega c3 should be the highest. Just write it down. Okay then. Now, same, repeat the same. So this should be, this is a table number, actually it's 3. So instead of writing this, I will write 3. This is a table number 3. So consider all the factors, 4 factors, 15 by j omega, 1 by 1 plus j omega, 1 plus j, 0.36 omega, 1 by 1 plus 0.09 omega. Okay. And in front of them, write down the corner frequencies. If they are for integral factor, there will not be any corner frequency, no need to write. So write the corner frequencies of the other factors. For 1 by 1 plus j omega, it is omega c1 equal to 1. For 1 plus j 0.36 omega, it is corner frequency 2.8. And for 1 by 1 plus 0 j 0.09 omega, it is 11.9. Now what is the slope of integral factor? It is minus 20. Okay, slope of integral factor is minus 20. Slope of this first order denominator factor is minus 20. Slope of this first order numerator factor is plus 20. For slope of this first order denominator factor is minus 20. Now Change in slope for the first factor will not be there. Write down this 20 here, minus 20. Okay, add with the 20 of the previous factor in the next section. Add with the slope of the that particular section. Just add it, you will get minus 40. Now write down this 40 in the next section. Add it with the slope of that particular section factor. So minus 40 plus 20, you will get minus 20. Now send this minus 20 to the next section and add that minus 20 with the slope of this particular section. So minus 20 minus 20, you will get minus 40. Okay, I hope you have understood. So for first factor, change of slope will not be there. So for the from the previous slope, write down the slope slope value of previous in this second column, second row, or second factor, I can say. So add it with the slope of that particular factor. If you add, you will get minus 40. After that, uh, whatever change of slope that you have got, you send it to the uh, next row, next factor row, and add it with the slope of that particular factor. You will get minus 40 plus 20, minus 20. And later, you send the slope of change in slope of the previous factor to the next factor column or row, and add it with the slope of that particular factor. Minus 20 minus 20, you will get minus 40. So I hope you have understood. Next, now let us consider low frequency and high frequency. Okay, so omega L should be less than omega C1 and high frequency omega H should be greater than omega C3. So omega L I have assumed 0.1 radian per second, omega H I have assumed 50 radian per second. Okay, so for compensated system, magnitude A in decibels. For compensated, I have assumed notation as A naught. So A naught is equal to G of J omega, G naught of J omega in decibels. So I have to calculate A naught for omega L, omega C1, omega C2, omega C3 and omega H. So let us consider omega is equal to omega L. A naught is 20 log 15 by J omega. Okay, so what is A naught? A naught equal to 20 log 15 by j omega. So what is omega? Omega L value is 0.1. So substitute 0.1. 20 log 15 by 0.1, you will get 44 decibels. A naught at omega equal to omega L is 44 decibels. Now let's go to the next. For omega equal to omega C1, A naught equal to 20 log 15 by j omega. So here once again, A naught equal to 20 log 15 by omega C1 is 1. So 20 log 15 by 1. Okay, 20 log 15 by 1. So you just simplify it, you will get A naught equal to 24 decibels. Okay. Similarly, consider omega equal to omega C2. So A naught is the formula for A naught is slope after first corner frequency. The formula will change. The formula is slope from omega C1 to omega C2 into log omega C2 by omega C1 plus A at omega equal to omega C1. Okay, that is the formula. So what is the slope from omega C1 to omega C2? Go to the table. From omega C1 to omega C2, what is the slope? Minus 40. Okay, so slope is minus 40. Where is this slide? Slope from omega C1 to omega C2 is what? Minus 40. And next, into log omega C2. What is it? Omega C2 by omega C1. What is omega C2 value? Omega C2 value is 2.8. Omega C2 value is 2.8. Omega C2 value is 2.8 and omega C1 value is 1. Omega C1 value is 1 plus A at omega equal to omega C1. A means here it is A naught, not A. Here it is A naught. Okay. So A naught at omega equal to omega C1 is how much? 24. Okay. It is 24. So just simplify this, you will get 6 decibels. Similarly, substitute omega to omega C3. So A naught equal to slope from omega C2 to omega C3. What is the slope from omega C2 to omega C3? From omega C2 to omega C3. What is the slope? It is minus 20. From omega C2 to omega C3, what is the slope? Minus 20. So 20 you are sending from here to here, isn't it? So it is minus 20. So minus 20 into log omega C3 value is 11.1 and omega C2 is 2.8 plus A naught at omega equal to omega C2. What is A naught at omega equal to omega C2? It is 6 decibels. So plus 6. Okay. So just simplify it, you will get minus 6 decibels. Okay. So I hope you have understood. Next, what omega equal to omega h, A naught equal to formula is slope from omega C3 to omega h. So what is the slope from omega C3 to omega h? So what is it? Omega C3. What is the slope? Change in slope here minus 40. That's you will send it to omega h. So minus 40 is the slope from omega C3 to omega h. That is minus 40 into log omega h is 50 and omega C3 is 11.1. So log 50 by 11.1 minus A naught. Okay. This is A naught. Okay, this is A naught at omega equal to omega C3. Just simplify it, you will get A naught equal to minus 32 decibels. Okay, now consider some notations. Okay, so consider some notations. And if you observe carefully, A naught value, first 2 points for omega equal to omega L 44 decibels and for omega equal to omega C1 24 decibels is same as your uncompensated system. That's why I have considered notations A points is just C. I have considered AB points. So even if you consider some other points, it doesn't matter. So consider whatever. Here we have got total 4 points. So I have written 5 points. Total 5 points. So I have written A, B, K, L, M. Frequencies omega C, L, C1, C2, C3, omega H. So same scale, 1 unit equal to 10 decibels on y-axis. Okay. So this is it. Now let us go for phase. So what is phase? Tan inverse of 0.36 omega minus 90 minus tan inverse of 0.09 omega. So why it has gone down? Let me see. Okay, so there is a gap here. So this is it. So you know how to write the phase angle. So it is tan inverse of 0.36 omega minus. There is an integral factor. So minus 90 minus tan inverse of 0.09 omega minus tan inverse of omega. So these two factors are denominator factors. This is numerator factor, that's why it is positive. This is integral factor, that's why it is negative. And since these two are denominator factors, these are also negative. So now let us consider different omega value, omega values. Okay. So consider, I will just increase the font size. Okay. Okay, I'm expanding this. So these are the different omega values, 0 0.1, 0 0.5, 1, 2, 5, 10. For that phase angles that I have got, you substitute in the above formula, you will get for 0 0.1 minus 94, for 0 0.5 it is minus 109, for 1 it is minus 120, for 2 it is minus 128, for 5 it is minus 132, for 10 it is minus 142. Okay, same scale as we have considered previous one. Okay, now plot the graph. Okay, we have the values. Now plot the graph for magnitude plot and phase plot. Okay, I have not, this is only magnitude plot. Magnitude for compensated system, you can see A, B, K, L, M. This is magnitude plot, and this is my phase plot. Okay, if you just draw it within 2 minutes. Within 5 minutes, I will conclude this topic. Within not within 2-3 minutes, I will conclude this. I will conclude this class within 2-3 minutes. Make it fast. You just draw it quickly as soon as you complete inform. Okay. So magnitude plot for uncompensated, magnitude plot for compensated, phase plot for uncompensated, phase plot for compensated. So let us consider phi GC naught is the phase of G naught of J omega at new gain crossover frequency omega GC naught. So phi GC naught is what? It is the phase at omega GC naught, and gamma naught is the phase margin of compensated system. Now once again, similar to our previous case, as we have determined the phase phi GC for uncompensated, now let us determine phi GC naught. How to determine phi GC naught? Go to the graph. Okay, go to the graph. Where is our plot? This is our plot. Okay, so from zero, this is our 0 decibels, isn't it? From here, draw a dotted line. You can see a dark brown line here. Dotted line towards your new phase, new magnitude plot. Okay, towards your new magnitude plot, wherever it intersects. Okay, from there, draw a vertical line towards x-axis. Okay, so you just observe the dark brown line here. From zero, draw a dotted line towards your new magnitude plot. Okay, wherever it intersects your new magnitude plot, compensated plot, magnitude plot, draw a vertical line towards x-axis, and it will, okay, Okay, it will intersect your compensated plot, phase plot at some point. So you can see here it is this brown line, dotted brown line is intersecting phase plot at some point. From there, draw a dotted line, what horizontal line towards the phase axis. You will get phi GC naught. Okay, you will get phi GC naught. I didn't mention here omega GC naught. Directly I have written phi GC naught here. If you want, you can even mention the omega GC naught. So how to get phi GC naught? Gain crossover means phase at gain crossover frequency. To get phase at gain crossover frequency, what you have to do is just consider go to the 0 decibel point. From there, draw a horizontal line towards your compensated magnitude plot. Wherever it intersects, from there, draw a vertical line towards your x-axis. Wherever it intersects your phase plot, compensated phase plot. See, compensated phase plot. Wherever it intersects, from there, draw a horizontal line towards your phase axis. Wherever it intersects on the phase axis, that point is your phi GC naught. Just locate that in your graph. Okay, I hope you have done. So phi GC naught you have got. Now if we know phi GC naught, we can determine the phase margin for the compensated system. So let us go. Mhm. Yeah. So I'm unable to see this cursor. I will take the laser so that it will be more easy for me. From the Bode plot of compensated system, 5GC naught, how much did you get? Minus 134 degrees. Okay, so what is phase margin of compensated system? 180 plus 5GC naught. 180 plus 5GC naught it is. Okay, so 180 plus 5GC naught. So 5GC naught is minus 134 degrees. So 180 minus 134, I have got 46 degrees. So in our question, what did they ask? They have told us that phase margin should be greater than or equal to 45 degrees. So how much phase margin did we get? We have got 46 degrees. Okay. So I'm taking, no, I'm sorry. I wanted the pen. Okay. So we have got phase margin of 46 degrees, which is acceptable. So this design is acceptable. Why? Because in the question itself they have mentioned phase margin should be greater than or equal to 45. We have got 46. So this phase margin is satisfactory. So phase margin of the compensated system is satisfactory and this design is acceptable. Okay. So I hope you have understood. If you have understood, you just mention in the chat box. Okay. If you want any changes or if you want me to explain any other topic, you just mention in the chat box so that I will explain it to you. That's it. Thank you for joining the class.